Okay, welcome everybody to today's seminar. So our speaker today is Akash Jain from the University of Amsterdam, and he will be talking about his recent paper on the fractons in curved space. So please, Akash, you can start whenever.
Oh, thank you very much for the invitation. It's really nice to talk here, and I hope I'm able to express some of my views on these new systems through this talk. And let's see how I go. So, okay, before I formally start, I just want to bring out a disclaimer that I'm not an expert on fractons. So if there are very pressing questions on fractons which you don't understand and you might be hoping that I'll be able to answer them, it might not be the case. Most that I know about fractons is from a couple of months, and I'm pretty sure I understand the problem I'm working at, and I'll try to convince you more about these things as I go ahead. But yeah, just to get that out of the way. Okay, so here is what we are going to be studying. So typically, we have, let's say you have a condensed matter system. Condensed matter system is like some lattice system with some local interactions. And it's commonly believed that if you go to some IR, if you go to some macroscopic behavior of the system in some continuum limit, this will be described by some local quantum field theory. I'm not sure if there's typically not a general proof of such a statement, but it's typically believed that you take, for instance, Ising model or take any lattice system with some local interactions, you will expect that there are some quasi-particle excitations in the long wavelength limit, and you can just focus on these quasi-particle excitations and forget everything about the microscopic details of the theory. But as it turns out, in recent years, by recent I mean the last 10 years, there have been some new models, there have been some new lattice models that seem to sort of violate some of our intuitions about quantum field theories. In particular, at least to me, the most exotic feature, or at least one of the most exotic features these systems have, are these things called fractons. These are weird excitations that once they are created, they cannot freely move in space. It's like not only, I mean, not move, not in the sense that they are in a potential, but rather you create like a free excitation, like a free fracton excitation, and then this excitation cannot just move in space. It will be present wherever you made it to be precise. There are other more exotic higher dimensional excitations. For instance, there are things called lineons that can only move in a line, or there are planons that can move in like a surface. And if you're in higher dimensions, then you can have higher generalizations of these things. And I think it's a fair statement to say that we are still trying to understand what these systems really mean, and how can you describe these systems in the continuum limit. Okay, one thing that I want to again get out of the way is that this is really an exploration about some fundamentals of quantum field theory and lattice systems. So far as I'm aware, there is no physical realization of fractonic excitations. So far, there is, I mean, the scope here is not to describe some physical observation that we have made and trying to find up quantum field theories for that, but rather it's a bottom-up approach where we are trying to see if these principles can be useful to understand more about quantum field theories and to understand more about these systems in general. But just a comment out of hand is that if I mean, there is a lot of effort going on presently in trying to construct these systems in lab. And if they are produced, and they have some very obvious and very elegant applications in quantum information theory. For instance, one of the biggest problems in quantum information or building quantum computers is building stable quantum bits. And stable quantum information storage. And this has found some really good applications in that if you can basically store your information in fractonic excitations, then your loss of information is much less because these fractonic excitations cannot move. So the decay due to interactions between nearby fractonic excitations is much less. But okay, this is not what I'm going to talk about today. I'm going to focus on some very small toy model So this is what the toy model that I'll be interested in will be. Just think of like a cubic lattice, and on that cubic lattice, on every link of that lattice, there resides a spin. So it's like just a spin half system. You can generalize it to higher spin systems, but this is a spin half system. It can take states plus and minus one, or you can think of it in terms of these Pauli operators here. So essentially, what I'm going to do is I'm going to take this spin system and write down some complicated 12 particle excitation or interaction. So this 12 particle interaction, what it does is that it takes every cube in your theory, which you can make, and then it creates an excitation, which is essentially a coupling between all 12 edges of that cube. And it's a complicated theory, it's a 12-body interaction, but sure. On top of that, we add 3 more excitations. These excitations are vertex interactions. So at every vertex, I take any plane. In that plane, on any vertex, there will be 4 spins. For instance, if you take this first one here, I have 4 spins in the YZ plane. And then I write down an interaction term for those 4 spins. And then I continue doing that for Y axis and Z axis. So there are these 4 interaction terms. You can also give like individual coupling strengths to each of them, which doesn't really matter. But this is a general class of what is known in the literature as X-cube models. And this is a topotypical example of what our fractonic systems are going to be. Okay, so this is just my setup. I have 1 12-body interaction and 3 4-body interactions in this theory. If you take this theory, by the way, this theory is particularly designed so that every term in the Hamiltonian actually commutes with itself. Of course, all the B terms commute with themselves. There is like not really much surprise there because B is made out of Z operators and all the Z operators commute with themselves. On the other hand, this A operator also commutes with B operators. I'm not going to do this simple algebra here, but you can just plug that there and you can see that A operator also commutes with all the B operators. So it's basically a totally commuting Hamiltonian. And since all the terms of this Hamiltonian are like commute with each other, this theory is exactly solvable. So you can solve this theory exactly and you can see what it gives you. And essentially, this is what it gives you. Without going into details again, what you find is that there is a very large number of ground states in this theory. Is that typically you will expect, typically in a condensed matter system, you will have certain ground states which will correspond to some configuration of spins. And then you can study excitations on top of that ground state. But as it turns out in this system, you have an exponentially large number of ground states. And what it works is that the number of ground states increase with the number of system size, or with the lattice size, or basically in general, the linear length of the system. And part of the reason why this is the case is that because this theory has a very peculiar subsystem symmetry. And the subsystem symmetry is given by essentially you take any particular plane in this cubic lattice, let's say this one, which I have denoted by blue, and you flip the spins in that entire plane. You can see that all the cube terms will remain invariant because any cube that is in touch with this plane has 4 of its spins flipped. So of course, since there are 4 spin flips, the cubic interaction is invariant. Similarly, you can see that at every vertex, there are either 2, 4, or none of the spins are getting flipped. So again, the Hamiltonian, the B terms are also invariant under this. So again, you can see, as I was talking about, there are these 3 terms, and since there are like either a 12-particle interaction or a 4-particle interaction, if you were to flip all the spins in a plane, it's going to be a symmetry. And this is what leads to really a large number of ground states, is that you can start with any given ground state, and then you can flip all the spins in any of the planes. And of course, if the system is in continuum, which is it has infinite size, you will have infinite such planes, or otherwise these number of planes will grow exponentially with the size of the lattice. And of course, you will have many more ground states corresponding to every action of the symmetry. And the last thing that is going to be the most interesting for us today is going to be the restricted mobility, in which these systems will actually admit some excitations that cannot move freely in space. So to that end, let me start with this picture here, is that I start with my lattice and I excite these bunch of Z operators, which I have denoted in red. Now, Z operators, if you will remember, are excitations, are the things that made up in the cube operator. And a Z excitation will excite a cube excitation. And of course, you can see that all the cubes, except on the vertex, the 4 vertices of this square-like or rectangular excitation membrane, has either 2 or 4 of its spins flipped, so it will not get excited. Of course, the only places where the excitation will get excited is at the edges here, where there is exactly 1 of the vertex or 1 of the edge that has been excited. So essentially, this excitation here is known as a fracton. So in other words, it's basically an excited state of spins in which the Hamiltonian is non-zero, or is at least is excited for 1 cube, or like this is this fracton. Now the interesting thing about this is that once you create this cube here, there are no local operators in the theory which you can use to move this fracton by itself. And that is, for instance, if you were to create a Z excitation exactly here, this will annihilate this cube here, but will create 3 more cubes at these places. And similarly, you can keep going. So whenever you create 1 cube or 1 cubic excitation like this, there is no operator in your theory that you can use to move this excitation anywhere. And you can move a pair of this. So if you take these 2 fractonic excitations together and you add like a bunch of membrane operators right in the middle of them, then this will move both of these from like one space to the right. So this is a general feature that these systems are going to have, is that an individual fracton cannot move, but a pair of them can move in some restricted way again. You can play the same game with these are the X operators that I had. With the X operators, the excitations that I'm going to excite are going to be obviously vertex interactions and not cube interactions. And you can take like a bunch of X operators acted like that, and you can see that the only place that it will excite the Hamiltonian is at the edges of these string of X operators. And again, once I create this string operator here, this has some restricted mobility. I can move it to left or right by introducing another X operator, either in front of it or behind this. And that makes sense, is that because it will increase the length of the string, and then it will move this linion or this vertex interaction in one direction. So that I can do, but I can again not move this linion either up or down or left, right, or anything. That is precisely because if I try to put another X operator here, this will not just move this excitation here, but it will also leave a residual interaction at this point. So this is almost everything that I want to say about this particular system. This is just supposed to be like a motivation, in the sense that this theory has some excitations that cannot move at all, or there are these linionic excitations that can only move in one direction. By the way, you can, as I just said, like you can create these dipolar interactions like this, and they can have some mobility. For instance, a dipolar excitation made out of 2 cube excitations can move everywhere parallel to its dipole moment, but it cannot move in the direction above. And similarly, you can take 2 linions and you can pair them up, and they can again move within a plane that is perpendicular to their dipole moment, but not along their dipole moment. And these excitations are known as planons. Okay, I mean, this is all some exciting thing, but this is the setup that I'm working with. I want to take this X cube model, for instance. This X cube model has these quote unquote quasi-particle excitations that once created cannot freely move. And I want to write down sort of a symmetry oriented quantum field theory for these systems, or rather I want to describe how I can understand the system in the continuum limit when I have a thermodynamic ensemble of such fractons, for instance. Okay, so the point of view of continuum description, these exotic features can be understood as some consequence of some dipole or multiple symmetry. As I go ahead, I'll make it more precise what I really mean by that. And then, of course, if the dipole moment is conserved in a theory, which I mean, you take, for instance, a charge particle, and if dipole moments are conserved, then a charge particle cannot move on its own. Because, of course, if a charge particle is going to move, it's going to violate its dipole conservation. But only a dipole of charge, or like a charge anti-charge pair, can move. And this is going to have similar features that we are hoping to describe. Okay, so let me get to some equations. So this is a normal U1 charge. So this equation, hopefully you guys have all seen like plenty of times. This is essentially a conservation law for some U1 density JT and some flux JI. And what that means is that if I integrate JT over some volume, and if I take time derivative of it, it will be given by totally a surface integral. So this is to say that the density JT is conserved. And what this means is that if I create like a excitation with some charge plus Q or minus Q, that excitation cannot decay on its own because the charge of the system is conserved. But of course, this excitation can move anywhere. That's fine, as long as the rate of change of the density is equal to the flux of the density. But on top of that, let me add this new requirement that my flux is given by the divergence of some symmetric tensor. This is, at this point, this is like a requirement. I want this to be the case. But if this happens to be the case, this is something that you can work out. Is that if you define a dipole moment associated with a particular charge, and you compute the time derivative of the dipole moment integrated over some volume, it will again give you a surface term. So what that essentially means is that you can again create charge particles. Charge particles are fine, but once a charge particle has been created, it cannot move because JT times Xi is conserved. So essentially you take any reference point and you compute the distance of the charge from that reference point, then of course this distance is going to change if this charge particle moves. So a charge excitation cannot move on its own. What you will also find is that you can create this sort of an exotic excitation, a vector charge or like a flux packet, and you will find that this flux packet is also conserved. So essentially, if you create like a sort of a flux, I mean, or basically see current moving in a wire as individual fluxes moving in some direction, then of course this flux can move in the direction of where the flux is, but the cross product of this flux is going to be zero. So which essentially means that flux cannot move in the direction up, or I mean cannot move anywhere perpendicular. So essentially if you take a wire of charge, in this theory the wire of charge cannot move up or down. It can only move along the direction of its flux. But in this theory you can create these dipoles. For instance, you can create a plus minus pair which has some given dipole moment. As long as the distance between these plus and minus doesn't change, then this dipole moment can move freely in space. Because of course, if you compute this dipole moment from any point, like it doesn't matter where it moves in space, the dipole moment only depends on the direction, on the distance between the two charges. So this combination can move anywhere in space. And the same is true for these packets. If you take like a wire with current moving in x direction and a wire with the current moving in minus x direction, and you couple them together, then the two of them can move anywhere in space. So this system is not exactly the same as the X-cube model I was interested in, because in the X-cube model, my dipole degrees of freedom could only move in the direction of the dipole moment, or sorry, perpendicular to the direction of the dipole moment. But okay, this is like a toy model that I can study, and there have been generalizations, and people know how to do this for more general cases as well. So this is what I shall be interested in. I have the so-called dipole symmetry algebra, which is you take the usual, these are all translations and rotations. So this is the usual rotations plus translations algebra, the Euclidean algebra, and then I have a time translation here. I have purposefully ignored a Bose symmetry, and you can sort of understand why I have done that, because in this theory, you cannot really have a Bose symmetry. And that kind of is obvious, because if you were to start with a state in which there is like an electron or a charged particle at some point in space, and if you boost it and start boosting it in some other direction, this is not an allowed state in your theory, because charged particles cannot move. So boost cannot be a symmetry of my theory, so I'm going to avoid that. So the first two columns here are essentially translations, rotations, some charge q, and some time translation by some Hamiltonian. On top of that, I'm going to add this new operator, which I'm going to call D. This is going to be the dipole moment operator. The dipole moment operator is going to commute with itself. So essentially, dipole moment in one direction is independent from dipole moment in any other direction. But these two non-trivial commutation relations are important. The first one is essentially just saying the dipole moment is a vector. It will rotate under the rotation generators Ji. The second one essentially tells you that momentum is not going to commute with the dipole moment if your state has some given charge q. And that again is kind of obvious, is that if your state had some charge q, then the dipole moment in a given state and in a state in which this state is moving with some velocity or with some momentum will not commute, because it has some charge q.
Akash, I have a question.
Yes.
So you're saying that boost cannot be a symmetry. Is it like a general statement, or I could imagine that in some like theories with like restricted mobility, there might be some components of boost symmetry that is like still present.
Okay. So yeah, I mean, so here I have taken my rotations to be a symmetry. So in that sense, my system is isotropic. And if the system is isotropic, then I cannot have any boost. But it is certainly possible that if your system was not isotropic, so your dipole was only conserved in some directions, and then you could have boost symmetries in other directions.
Okay, thank you.
But right now, I mean, if you have Ji's as an operator, which is essentially telling you that system is isotropic, then you cannot have boosts. Okay. Cool. So, okay, moving ahead, there is a conservation law associated with each of these operators. Hamiltonian, momentum, and charge has the usual conservation equations, which are energy conservation, momentum conservation, charge conservation. But in addition, Ji leads to angular momentum conservation, that also is probably we are very well aware of. But finally, this is the thing that we were talking about before, is that dipole moment essentially leads to a conservation of dipole moment. This is a very simple example of such a theory due to Petko in 2018. This is a scalar field theory for some scalar field phi, and this is the Lagrangian. The Lagrangian has a non-relativistic time derivative term, like a Schrodinger theory. It has a potential, but it has this weird term here. And this weird term has been designed so that this theory is invariant under U1 transformations. So it's a complex scalar field theory, so it is invariant under U1 transformations, but it's also invariant under these exotic transformations, where essentially the phase of the U1 transformation can depend linearly on space. It cannot depend arbitrarily on space, but it can depend linearly on space. And then you can kind of see where this comes from. This essential combination here, which is a bilinear double derivative combination, is precisely defined so that it transforms covariantly under both of these transformations. And this so-called kinetic term will now have 4 spatial derivatives rather than 2. So this is again something that shows up in these theories quite often, is that these theories don't have the conventional k-square scaling of the Lagrangian. They will have k to the power 4 scaling in this particular case. Now this particular theory okay, I've given you this. So I mean, this is invariant in the U1 transformation. So you can go ahead and compute the Noether charge or Noether current associated with the system. After performing the Noether procedure, you will find the case to be the following. You will have a density. The density is the usual density phi star phi in such a theory. But in addition, what you will find is that the flux of this theory is given by the gradient of a symmetry tensor, just like we talked about before. And then, of course, in this theory, whenever you create a charge excitation, that excitation cannot move in space because the dipole moment is constant. Okay, I'm interested in more like field theoretic properties of the system. So what I'm going to want is I want to gauge this symmetry, or rather I want to introduce some background gauge fields so that I can probe these currents by varying these background gauge fields. So this is my proposal, or I mean, okay, not my proposal, this was done way before, but my proposal in this talk is that I'm going to introduce three gauge fields. AT and AI are the usual gauge fields, and they will transform by usual by a d lambda term here, and this will lead to the U1 transformations. But in addition, I'm going to introduce like a symmetric gauge field, and the symmetric gauge field along with this vector gauge field here will transform with some vector parameter psi I. And this vector parameter, I mean, you can go and quickly check that if AI couples to Ji and Aij couples to Jij, then this precisely leads to the conservation equation here that I mentioned. Just an aside, I'm being a little over here. You can also gauge fix the size symmetry completely by setting AI equals to 0, and then you can just work with a scalar potential AT and a symmetric gauge field Aij. But I'm going to find it useful to keep AI as well. Okay, but once all is said and done, you can take the same scalar field theory that I had before, and you can define a time derivative, a covariant time derivative, like you do in usual gauge theories, and space derivatives. But then this Dij combination that I had defined before will be given by the same, but instead of partial derivatives, you have these symmetric covariant derivatives now, and you have this Aij term here. And this is not something I'm going to do, but you can take the system here and you can convince yourself that it transforms covariantly under all the transformations that I talked about. But the nice thing about this is that once I've done that, I don't have to go and do the Noether procedure. I can just take this action, vary it with respect to the three gauge fields, and read out the three currents. And that you can check will work out to be exactly that we found before. What I'm going to be more interested in is what happens when you try to make these gauge fields dynamical, or rather, what happens if you try to couple the system through some electromagnetic fields. Now, one thing that you can clearly see is that if you were to define electric fields and magnetic fields like you usually would, which is just using this A mu, and you have some F mu, and then space and time components of it will give you some electric field and magnetic field. These two objects are not invariant under the dipole symmetry transformations. They're by definition invariant under gauge transformations, but they're not invariant under dipole shifts. And so a usual Maxwell's kind of action that you would write in normally in, for instance, QED will not do the job here because it is not dipole invariant. And physically, you can think of this as if you start with a dipole with some plus and minus charge and you apply some electric field, then this is not good because this electric field will take plus charge and move it along it, and take the minus charge and move it away from the electric field. So it will tend to break the dipole. We don't want that. So I cannot couple this system to usual electromagnetic gauge fields. What I can do, however, is try to define something slightly more fancy. So let me define something that I call a dipole gauge field. So a dipole gauge field will be defined like this. It's essentially the field strength or electric and magnetic fields from before, but I'm going to use this combinations of Aij, which was a symmetric gauge field, so that this new gauge field here, where mu runs over time and space index, now transforms almost like a gauge field for this side. But if this is a transformation, then I know precisely well how to construct invariants. I can construct an invariant like this. So this is just an anti-symmetric derivative of this A mu k, And of course, this combination will be invariant under this transformation. So this new guy here, Fk mu nu, is invariant under both monopole as well as dipole transformations. Now, if once you have that, then it just becomes a tensor counting exercise to create an action. So you can define something known as, electric field or dipole electric field, which is essentially some components of this Fk mu nu, and similarly you can define a magnetic field, and you can write down something like that. So this is the dipole generalization of Maxwell's theory, if you will, and you can construct similarly the Maxwell's equations. These are the Maxwell's equations. I don't have much intelligible to say about this, except that they are the generalizations of Maxwell's equations in usual electromagnetism. But more importantly, they are invariant under dipole symmetry. So you can take a dipole symmetric system and you can couple it to these gauge fields in a dipole invariant manner. Okay. This was mostly what I wanted to say about dipole symmetries and fractonic spacetime, fractonic systems in general. Now I want to do something more, slightly more technical, is that I want to couple these spacetimes or couple these backgrounds to some, couple these systems to some background spacetimes. And the reason for doing it is, of course, twofold. First is like, it will teach me how to couple fractonic systems to a curved spacetime, in, for instance, on the surface of a sphere or some time-dependent background and whatnot, which has its own applications. But more theoretically, this will allow you to define or compute covariant currents, or compute energy density, momentum density, and current, and those space-time Noether currents associated with the system by varying the background fields. So this is what I'm going to try and explain now. But before I go, I need to take a small detour and into what are known as Aristotelian spacetimes. So as I was talking before, these systems do not have a boost symmetry. So you cannot really couple them to usual spacetime metric, G mu nu, because spacetime metric will assume invariance under Lorentz boost, and that I do not want. So rather, I have to do something more fancy, and which is the following. I want to introduce some component, this is known as a clock form, and mu is going to couple to energy density and energy flux. And you can really think of this as a GTI components of the metric. Then I have a spatial metric, H mu nu, which is going to be the Gij component of the spacetime metric. But more importantly, I now also have a frame field V mu. So this is because my system does not have any boost symmetry. So whenever I define background spacetime, I also have to accompany this background spacetime with the notion of a preferred frame of reference, which is not there in Lorentzian spacetime. And of course, I can also introduce a gauge field for my U1, but that will just go along for a ride. All of these fields that I've introduced here are not all independent. They follow some normalization conditions, but at the end of the day, if you solve all those normalization conditions, what you're going to find is that these are the independent components. You have NT and NI, which are like GTT and GTI. In relativistic theories, Hij is like Gij. Vi, as I said, is like a frame velocity. AT and AI are the usual gauge potential and vector potential. You can go to the flat space limit. Flat space limit is essentially going to be NT equals to 1, which is essentially saying GTT equals to 1. Hij is delta Ij, and everything else 0. This is just some notation, which I will find it useful. You can define covariant derivatives in the spacetime. These covariant derivatives are defined to satisfy these properties. This is not extremely important, but I just want to mention in case you get shocked when I start using Neblin in the next slide. Okay, so what I'm going to want is, this is essentially the whole point of this exercise, is that when I couple my system to some background.
Sorry, Akash. I just wanted to tell you that you have 10 minutes left.
Okay, all right. All right, so the whole point of this exercise is that I want my theory to be invariant under some transformations of the background fields, and this will essentially amount to the systems having some global symmetries. So I want the system to be invariant in the Lie derivatives of all my fields, which essentially corresponds to your system being invariant in the space and time translations. And in the case of mu, I want it to be invariant under some gauge transformations as well. And given a parameterization of some partition function or some generating function like this, you can use this to derive the Ward identities. So these are the Ward identities for some energy current, some momentum current, and some charge current. And this is essentially a fancy way of writing these things in flats. In curved space, this essentially corresponds to some energy conservation, momentum conservation, and charge conservation that we talked about before. Okay, this is an aside that I think I can skip. But okay, the whole point was to, okay, this was just the aside, and now I want to do this for a system with dipole symmetries. So I want to talk about this mu, but now in addition, I want to introduce this new vector field, this new symmetric tensor field, mu. This is symmetric and this is purely spatial, so that when you contract it with the background V, it will give rise to 0. And I introduce this new gauge field, and I also introduce this new symmetry parameter psi mu. This is essentially the curved space generalization of the symmetry transformations that I did before. And once you do that, you can kind of check that now if you define a G mu nu coupled to this new gauge field A mu nu, you will give rise to this identity here, which is essentially the curved space generalization of a dipole Ward identity. This is also kind of an important point, is that once you are able to define energy density, momentum density, and stress tensor in this theory, you can ask how do they transform under these dipole shift transformations. And this is how they transform. Basically, in a flat space, you will find that energy density and energy flux can be defined without any problem, but momentum density cannot. Because momentum density is not dipole invariant, it transforms like this. And this again sort of makes sense, because if you are in a state with non-zero density, non-zero JT, then of course momentum will not be invariant, because of course, I mean, a flow of a normal density is not invariant in our theory, because we are not allowed to move our particles. And the same is true for stress tensor as well. Okay, so I just want to circle back to the scalar theory that we had. You can take the scalar theory and you can just write down some fancy version of it, including some background gauge fields and these background electromagnetic fields and background like Aristotelian spacetime sources, and you will find this. I mean, this is again not extremely illuminating at this point. This is essentially writing it in some covariant version. And this d mu nu operator, for instance, now becomes something much more complicated. But the whole point of this exercise is that now you can take this system and vary it with respect to all the sources and read out all the background, all the currents and so on. So I'm not going to bore you with explicit details, also that knowing that I'm short on time, but this is something that I do want to point out. And this is kind of an important point, is that before I had defined this gauge field, this dipole gauge fields, which is some transformation that look like this. I can try and do that in curved spacetime, and it turns out that the curved spacetime generalization of this gauge field that you can make actually does not transform nicely under these dipole shift transformations. So it has a piece that goes similar to before, but now there is this additional piece that corresponds, that depends on the derivatives of the frame velocity. So essentially, if you are in a background in which your frame velocity is dependent on space and time, then this generalization of the dipole gauge field is not going to transform covariantly anymore. This has some very important consequences, is that previously I could define an Fk mu nu, a dipole field strength, which transformed covariantly under both the transformations. Now this is no longer going to be the case. You can define this rank 3 tensor F lambda mu nu, which is a really generalization of this Fk mu nu that I had before. but this guy now transforms very non-trivially. So these things appearing here are some quantities that I haven't defined really, but they are some versions of space-time curvature and things like that. And what you end up finding then is that a natural generalization of this symmetric tensor gauge theory that I had before is no longer gauge invariant. So, I mean, so in other words, if you were to take this free electromagnetism generalization of two like dipole symmetric gauge fields, then such a theory is you cannot consistently couple to curved space. What you can do as an aside is that you could define something by if you couple this theory to some matter fields. So by itself, this theory is not allowed, or this theory does not transform covariantly into space-time transformations. But you can define something like this. This combination is some weird combination, but you will have to trust me when I say that this combination, including some matter fields, does transform covariantly under all the transformations. And if you linearize this theory, then this will give rise to the same kind of symmetric tensor gauge theory I had before, plus a bunch of interactions. So essentially, this is all really saying that you could not have massless gauge fields with dipole symmetry, but you could have massive gauge fields when you spontaneously broke the dipole symmetry by introducing some matter fields. So you can have gauge fields, but then there will be additional terms here which will give rise to mass terms for all the gauge fields. Okay, so seeing that I'm almost out of time, I'm going to just end here. What I have described for you is some continuum description of Fracton models, or trying to like describe some symmetry principles for fractonic systems. And essentially, we talked about some dipole or multiple symmetries that will give rise to these fractonic behavior. We learned how to couple these systems to some conserved dipole or multiple moment in curved space-time. Importantly, an important feature here was that there is no boost symmetry in these systems, so you can only couple them to Aristotelian space-time. So rather, your space-time must carry a preferred frame velocity. Otherwise, you cannot couple them. But a consequence of this turned out to be that like this frame velocity leads to the symmetric tensor gauge theory, which was the free version of electromagnetism in the presence of conserved dipole moments. And this system is not typically conserved or typically cannot be coupled to a general space-time. And okay, thank you very much. I don't know if you have any questions.
Okay, thank you very much for the nice talk, Akash. So it's time for questions. So if someone in the audience has a question, please unmute yourself. And
maybe I have a question about this massless versus massive. So
yeah,
do I understand correctly that this is motivated by a physical system that you want to study?
So I mean, so the physical system, I mean, okay, I'm not sure about the physical system, but this is motivated from the X-cube model, really. So this is essentially saying, so the X-cube model, as it turns out, I haven't really talked about this today, but X-cube model does have its dipole symmetry spontaneously broken. So the system can describe the X-cube model, and in fact, this is the X-cube model. So, or rather, in some limit. But what I'm really trying to say is that you cannot, I mean, it's not possible to have a theory of fractons with gapless excitations. So excitations always have some mass. So you cannot have a gapless theory, or at least this particular theory, which is supposed to be the U1 symmetric tensor gauge theory. This theory cannot be consistently coupled to curved space if gauge fields are massless.
Okay, thank you.
another question?
Yeah.
Can I have a question as well? So when you gauge your action, you introduce those gauge fields. So that's yeah, right here. So that's not a unique way to gauge it, right? There's another way to gauge it when you would just have two gauge fields and then a different transformation property for the.
Yes, so that's a special case of this. As I said, that you can always, so since you see that AI transforms linearly, in psi. So you can completely gauge fix psi by setting AI to 0. If you set AI to 0, then psi just becomes minus grad lambda. So essentially, in that case, you just introduce one scalar gauge field which transforms like this, and one symmetric gauge field which transforms like this, where psi is given as grad lambda.
Yes, but you can have like in the Fracton gauge principle paper, which you then Predko is actually showing a different way to gauge fractons, which is that the transformation property for Aij would be like a partial, would be double derivative. Instead, I mean, you have mixed derivatives of first order, and here's a second order.
Yeah, I mean, that's what I'm saying. If you take psi equals to grad lambda, then Aij.
Oh, okay. Yeah, sure. Yeah, okay, I get that. Okay, so
yes, that's just a special case of this.
Okay, so that's more general. Okay, and then when you introduce v, so is that like a velocity field? Is that correct? Because it seems to me
it's velocity, but it's like a frame velocity. So it's like a velocity which is a property of the observer and not of the system.
Because you say it's 0 in the flat space.
Yes, so that's why so I'm defining the flat space like this, but rather you should think of v as some background velocity, or rather velocity of the observer who is observing the system. So just like Hij is the spatial metric of the background or of the observer, or like wherever the system is coupled to. Similarly, v should be thought of as the velocity of the observer. So I mean, it's the same thing. I mean, in Lorentzian systems, you can also define a velocity, but like a background velocity, but then system is invariant under Lorentz boost of this velocity, which is essentially saying that it doesn't matter which observer is doing the measurements. But here it does matter. So the system will non-trivially depend on v, so it does matter who is doing the observation.
So is it always true that the velocity needs to be 0 in the flat limit?
No. This is exactly. I mean, I'm just defining flat limit to be the case where I turn everything else to 0, but no, it doesn't need to be.
Okay, so you could have non-zero velocity, and this would still work.
Yeah, you can. Yeah, so I mean, so everything that I showed was for everything non-zero. So my curved space is really saying that all of these things can be whatever they need to be. But you can also specialize to the case where you set everything else to trivial, but you keep vi non-zero. That's completely fine. This is like saying that you couple your Fracton system, but you observe your Fracton system from a reference frame that is moving.
And then the energy would not be conserved, and then.
Yeah, of course, and energy will not be conserved, because if you have a velocity, then the derivatives of the velocity will give rise to this pseudo power contribution. And similarly, momentum will not be conserved because there will be a pseudo force contribution. So,
okay, so your system is dependent on v. It's different v.
Yeah, because my theory does not have any boost symmetry by definition. So that's why my conservation equations will depend on v.
Okay, thank you. So maybe last question. So would your momentum just be like some coefficient times v in this case?
That really depends, because I mean it will depend on what system you're talking about. So what you should read, I mean, but what is true is that momentum will be, you take your Lagrangian and you vary to respect to velocity, and you will get the momentum, but it doesn't really need to be some coefficient times v. It can in general be like, for instance, in the Predko theory, I haven't given the expression, but in the Predko theory, you can, for instance, take this weird guy here. If you perform a variation with respect to velocity, you will get the momentum as psi star d mu psi, for instance.
Yes. Okay, thank you.
Okay, I have a question that is also related with these word identities.
Yeah, okay.
So you told us that you cannot construct gauge invariance because you cannot, because the field strength will not be gauge invariant.
Yes.
So, and then in your, should that effective function or partition function, whatever, is something that you obtain once you have integrated all the matter fields. So, and you are assuming that is, and therefore it has to be like a functional of the gauge fields and gauge fields and the geometric data. But
Yes.
you don't have invariants.
Yeah, so
You don't have invariants, so and you're assuming actually that the partition function is invariant to derive the word identity. So what's going on there?
So basically what I was saying is that I want a theory that is invariant in the space-time translations as well as some dipole symmetry. And what turns out to be the case that, for instance, the Pretko theory, this theory does the job. This is invariant in the space-time translations. It is also invariant in a dipole transformation.
No, right, but that, I mean, that's not that I can get. But my point is that just like from the low energy perspective, in which you have just integrated out all the matter fields, that now you don't have a phi field because you, and then I just try to write some like effective or generating functional, let's say, that will be just a function of A, H, and I mean all the geometric data and the gauge fields.
Yes.
Okay, but there are no gauge invariants you can construct. So how can you assume that the partition function is invariant under under gauge transformations to derive the word identities?
Okay, so really, what I'm saying is, I mean, so okay, I don't know if you will be able to derive word identities or not, but this is the case that if my generating, so really the one way to see symmetries is that a certain symmetry should be thought of as you perform certain transformations on the geometric data or on whatever your fields are, and you can see that as like really I mean, or it's an invariance of the partition function. So I mean, okay, unless I'm not understanding your question, I believe what you're saying is that you have integrated out all the gauge fields, so now you
no the gauge fields, because let's suppose the gauge fields are background gauge fields, not dynamic.
Okay, sure. So if
and you integrate out the discharge field that you were talking about. You integrate out the charge field, and then you have a functional of all the geometric data and the gauge fields.
Yes, so now you have function of all the geometric data and gauge fields. So now you can vary your partition function with respect to this data and get all the operators. And those operators will satisfy this word identities provided.
But if there are no gauge invariants, how the partition function can be gauge invariant?
Oh no, so this is what I said, that I mean the system will not be gauge invariant if your background fields were, I mean if you wanted to make your background fields dynamical by adding these terms here. So for instance, if you wanted to make your system dynamical by adding this particular term here, then the new theory will not be gauge invariant. Does that make sense?
So is it like you cannot have interaction for the gauge fields in this case? Or...
No, we're not talking about interactions on the gauge fields. So
no.
I don't know if I agree with that.
Okay,
because the point is, because I will just maybe give a chance to other people to ask questions, and maybe we can discuss that after we officially finish the talk. So is there any other question in the audience? Okay, if not, we can like officially thanks Akash again for the nice talk. And then I will finish like recording.